Today, the goal is to connect complex numbers with polar numbers, both of which we've been working with recently, and try to do some calculations using polar numbers as a means to a shortcut. So to begin, we actually need to review the relationship between rectangular coordinates and polar coordinates in the first place, because when we were plotting complex numbers, we were plotting them in a way that resembled the Cartesian coordinates. So the method for converting between the two systems is going to be nearly identical. Here on the screen, I have our equation bank that is all the relationships we could come up with that connect a rectangular coordinate system and a polar coordinate system based on this triangle. I've also already done one of the questions so that we can see that and mimic it in a second example. So the goal here was to turn the coordinates that were given as x and y and change them to r and theta. R is the hypotenuse of the right triangle, so to find that we just do Pythagorean theorem. And the theta can be found at that point using sine, cosine, or tangent. Does not really matter which one you do. In this first example, I got 2√5 as the r and 63.4 degrees as the theta. Let's do a second example. We have the point 1, 2, which is in rectangular coordinates. That's the x and y. And I think the first thing to start with is the r. It seems to be the easiest. It doesn't take any extra thought or work or any knowledge of where the point is located at all. So set that up using Pythagorean theorem. And then simplify. Looks like in this case our r is √5. Then I'm going to follow up with tangent to find the angle. Remember, when you're trying to ask a calculator for the angle, you need to use inverse trig because you don't know the angle, so you can't type it in like you would for normal trig. So I'm going to use tangent inverse for this. And by typing in tangent inverse of 2, I also get 63.4 degrees. That means as we go to write our ordered pair as a polar ordered pair, we would put √5 first, and then 63.4 degrees next. How we're going to convert from a complex number to a polar number is going to be very, very similar, because the way that we were plotting complex numbers, a plus bi, was on a rectangular axis, although not the same as the Cartesian axis because we're plotting a single number, not an ordered pair of numbers. It is still rectangular in nature, so it still fits the right triangle diagram. In this case, a is our x and b is the y, so I'm using very similar equations to the ones above, but just a and b instead of x and y. So let's go ahead and practice that first before we even talk about the polar form of the complex number and all the stuff in the box. So in this first example, I have the complex number -3 plus 3√3i. I've even drawn a picture of it so that we could see where the angle is going to be located. And so you can see here, I've already set up r, the equation for r, because that's usually a good place to start as a first step. So we're just doing Pythagorean theorem to find the r. Let's go ahead and simplify that Pythagorean theorem. I do have a tip. When you get to the number with the root inside of it, as long as the numbers inside of the square are multiplied together, that makes them a single term, then you can distribute the square. So I'm going to think 3 squared, 9, and then √3 squared gives me 3. And that's just an easier way to tackle squares when there's a root inside. Continuing to simplify, and I get 36 for r squared, which makes r 6. So now it's time to find the angle. Now the way you find the angle, you need to be a little bit strategic. We were talking earlier about using tangent to find the angle, but really it depends on what quadrant your point is located in and what other work you want to have to do once you find the angle in the calculator. You have to recall from the fall that tangent inverse can only identify angles in the first and fourth quadrant. That is the same for sine, and cosine inverse can identify angles in the first and second quadrant. So if our angle is in the second quadrant, tangent is not going to be able to locate it. It's going to give us an angle in a different quadrant, and then we have to use our knowledge of where we are plotting this point to work our way back to the correct angle. In any case, no matter which trig you use and which quadrant you're in, the angle we're looking for is measured from the positive x-axis counterclockwise, just like you would measure on the unit circle when we first started working with angles. In this case, because of the quadrant we're located in, I think it would be easier to use cosine inverse because cosine inverse can handle angles in the first and second quadrant, so it should just give us the answer right out of the calculator. So let's do that for this question. For this question, I got 120 degrees, which matches our location with our point being in the second quadrant. Let's look at what would happen if you had used tangent, just so we can troubleshoot that issue. If we had decided to use tangent inverse using opposite over adjacent, this is the relationship I would have typed into the calculator. So let's go ahead and see what that gives us. Notice how in this case the calculator gave me negative 60 degrees. The reason it gave me negative 60 degrees is because the calculator has no idea whether your negative sign that you typed in was in the numerator, the denominator. All it knows is that it can only give you angles in the first and the negative fourth quadrant, and this combination of a positive and a negative x and y leads the calculator to believe our angle is in the fourth quadrant. And it always gives us the angles in the fourth quadrant as negative. So I'm going to draw the picture of what it's doing so that we can understand why it gave us negative 60 and how we could have used that to find our angle anyway. So here's a drawing of the negative 60 degrees that our calculator gave us. It is the exact same size triangle as the triangle that we have. It even has the same ratio of sides, but it's just in a different quadrant. That negative 60 degrees tells us that the size of the triangle itself is 60 degrees. The negative meaning that we just went clockwise instead of counterclockwise to get there. So I can still carry that number over to my drawing, and it still represents the size of the triangle, but I just need to know that the entire half of the circle is 180, the little triangle wedge is 60, and the difference between those two is the angle I actually want, which is the measurement from 0 up to the point, but not past it. 180 minus 60 gives us the 120 that we got from the cosine anyway. There is no formula that will work for all angles in all quadrants for all points. So each time, if you're getting an angle that you're not expecting, draw a picture. Then you can see whether you should be adding or subtracting angles like 90 or 180 from the one that you got. However, if your point lands in a quadrant that you know is associated with one of those inverse trig functions, you can use that and it will give you the answer outright. In this case, the 120 degrees came from cosine without any additional work. Okay, now that we've made that really complicated, let's move to the second one because it is super quick, especially now that we understand r and theta are just measuring distance from the center and angle from the positive x-axis. In question number 2, you can actually get both of those measurements just by drawing a picture and looking at it instead of doing any calculations whatsoever. So in number 2, I've already rewritten this imaginary number as a complex number. The real part is 0. So when I go to graph it, it has no horizontal movement and it's down 3 to get to that point. R is measuring the distance from the center to the point. So it is 3 units down from 0. The angle, again, is measured from the positive x-axis around to the point. In this case, that angle would be 270 degrees. Now that we've figured out the polar parts of each of these complex numbers, let's go back to the box and see what the complex number looks like in polar form. So here in the box, I have a few things that look really complicated. So I'm going to explain where they come from and then how you can shortcut the way you write them. So this right here is the polar form of a complex number. It looks really complicated, kind of gross, but it actually comes from some calculations we've already done. So looking to the side over here, right above my drawing, I have the complex number a plus bi. I'm going to then take the equation that we use to find a, which is r times cosine. That comes from back up here when we were originally converting from rectangular to polar form. And I'm going to replace the a with r times cosine. And then I'm going to do the exact same thing with the b and replace it with r times sine. And at that moment, I have now changed the complex number from rectangular coordinates that tell you how to plot it, a and b, to polar coordinates that tell you how to plot it, r and theta. But they're in the exact same place that they were before because we're not writing an ordered pair, we're rewriting a single complex number. So now that we know where that comes from, let's look at some shortcuts for how to write it because it is really long and you don't have to write it really long each time. MathXL's favorite way to write complex numbers as polar numbers is actually the middle notation that you see here. So the only change made here from what we had before was that they took that double r and factored the r out. So MathXL will typically write this in your homework, but it will leave you with boxes to fill in. So the form is actually pre-made, and you just have to know that the first box is the r, and the second and third box are the angles. And it's the same angle for both. The fact that that is the same angle is actually what leads us to the shortest shortcut for writing polar form of complex numbers, which is this notation here. In this case, we are only writing the angle one time because it is the same angle anyway, and the CIS stands for cosine I sine. So it is the shortest way to communicate the R value, the cosine I sine, and then the angle. So you are welcome to use any of these notations, but just know MathXL uses the one in the middle. Okay, now to see why we would even want to work in polar form at all. There happens to be a series of theorems. They're basically formulas that you plug numbers into that can do some of the algebra for us in a much easier way. We're going to compare the algebra that we've been doing with complex numbers, like last class, and this new method to see how they compare. So here is the first set of theorems. We have a formula to follow if we're multiplying two complex numbers to each other, and then also a formula for when you're dividing them. The good news is these formulas are almost exactly the same, and the differences between them are kind of easy to remember if you associate multiplication with addition of things and division as subtraction. The formula, although it looks really complicated, breaks down into two parts. When you're multiplying two complex numbers, you multiply their r's. Whatever you're doing to the complex, you do to their r's. And then you add the two angles. That's the only two new pieces, and then you put it into polar form. It's creating a new complex number, which is the result of multiplying those two numbers together, and then you put that into polar form. When you're dividing, you divide the r's and subtract the angles. So I'll show you how quick that can be because it really doesn't have to be that complicated. Below, I have two complex numbers. I've already figured out the r and the theta for one of them. So we're going to practice the second one together. And then we're going to multiply and divide. Let's first figure out z2 together. So to find the r value for a complex number, we're doing Pythagorean theorem. So I'm just going to set up Pythagorean theorem with the parts or components of z2. Remember, we're not plugging in the I into this Pythagorean theorem because the I is only there to tell us which part of the number is A and which part is B. It tells us that the coefficient of the I is the B, and that's what we actually want to use. I get that R is 2 for Z2. Now let's move on to the angle. I'm going to use tangent for this one. I can tell that if I were to plot this point, it would be in the first quadrant because it's a positive x and a positive y. So it really doesn't matter which trig I use. I'm not going to get tricked by any negative angles or anything like that. So I'm just going to use tangent. And while we're going to the calculator, I just realized I did not find the angle for Z1 yet, so let's do both of these at the same time. Okay, so for Z2, as suspected, it just gives us a positive angle with no problems. And for Z1, because it gets plotted in the fourth quadrant, tangent inverse is giving us a negative angle. I actually don't really care. For this part of the work, we're about to do something with that angle, so I'm not going to bother turning it into a positive angle unless I need to do it later. Because sometimes, as you'll see, the work will fix the negative angle for you. And so it might actually be less work to leave it alone until you're completely done with the question. Okay, so now we're going to put these parts together and do the product Z1 times Z2. Here was the pattern again. The pattern said that we're going to write our complex number in polar form where you multiply the r's and you add the angles. So looking at our two r values, which I'm highlighting in gray, multiply them together, 4, and that's your new r value for the product Z1 times Z2. So the new r is going to just be 4. For the angles, you're going to add them together. So negative 30 plus 60 gives me a new angle of 30 degrees. Now that we've followed the pattern, our last step is just to put these numbers into polar form. And there were 3 correct forms to put this into, so it's completely up to you which one you want to use. I'm going to stick to the one that matches MathXL's expectations, so that way our notes match what you'll have to do for your homework. So for that method, we're going to write 4, and then parentheses, cosine 30 plus I sine 30. The angles will always match, always. And MathXL is going to have 3 empty boxes for you to enter your numbers into. So you will type in 4, and then 30, and then 30. Now I want to compare this with the same work, but done using algebra that we did last class, which was keeping the complex number in rectangular form. So I'm just going to scroll to the side. I already have this part done, so you can just watch. Over here, I have Z1 times Z2, which we've done before. I wrote each of the 2 complex numbers side by side and then distributed. So basically FOIL. And then by the second turn, I combined these 2 into 2i, and then changed I squared to -1, and then combined these 2 into 2 root 3, and that's the result that I got in rectangular form. Now that actually turns out to be the exact same answer as our answer in polar form, even though they look completely different. So right below that, I have copied over my answer in polar form, so you can see them side by side. These are the exact same complex number, just one is written as if we were moving along the x-axis and the y-axis, and the other one is telling us the directions for going around the circular grid of a polar graph. And you can even convert between the two of them very easily to check your answer. So right below this, I have changed it back to rectangular form just to prove that these two really are the exact same number. So I'm turning this polar form back into rectangular form for no particular reason other than to verify that I did actually get it correct. To do this, I'm just replacing the cosine and the sine with the values that they have. So using a unit circle, cosine of 30 degrees is root 3 over 2. That's the x coordinate at 30 degrees. And the sine of 30 degrees is 1/2. And then if I distribute the 4, we get the exact same answer that we had using regular algebra. So this is just proving that this theorem actually does work. It gives us the same value, it's just that our answer is in a different coordinate system. Why you may want one over the other completely depends on how the information is given to you. Using this new theorem is way easier if the numbers are already given to you as polar numbers. Yes, it was a lot more work to change it to polar first and then multiply, so that's not really the practical application here at all. The only reason I'm asking us to do both is to practice converting, practice using our equations, and then also to get a chance to use this theorem. Let's go ahead and complete this section by using the theorem to find the quotient, z1 divided by z2. This should be very fast. The pattern was, if you're dividing complex numbers, you're going to divide their r's. So their two r's were 2 and 2. When we divide them, that gives us a new r value of 1. And then you subtract their angles. Now make sure you do this in order. Order of subtraction is very important. It's going to be z1's angle minus z2's angle. So z1 was negative 30 minus 60. I get an angle of negative 90. Now in question 3, the negative 30 plus 60 added up to a positive angle. It was great. It actually fixed the negative angle for me. I didn't have to do any extra work. In this case, the subtraction made our angle negative. And the directions do say that we want the angle to be between 0 and 2 pi, or 0 to 360. So I need to convert this to a positive angle before I'm done. The easiest way to convert an angle from negative to positive is to use coterminals, which means we're going to add one full circle to this angle. So I'm going to add 360 degrees to basically just be in the same spot, but just write the angle in a positive way. I'm going to get 270 degrees. So now to wrap this up, let's write this in polar form. R cosine plus I sine theta. At this point, I recommend taking a break. So maybe pause the video, take a moment to breathe and think about what we've done so far, because we're about to get into some more complicated theorems using the polar form. Okay, now we're finally getting into the theorems that are the name of this set of notes, DeMoivre's theorem. There are actually two parts to this theorem. They are both related to exponents of complex numbers. So this is if you want to do some math with a complex number, and this is really where you actually would want to change the number to polar before starting. So imagine that I asked you this question number 5. 1 plus I to the 20th power. Feels ridiculous. That's because it is. If you were to do this by algebra that we have just talked about, leaving it as a rectangular number, you would have to write out 1 plus I 20 times and distribute it over and over and over again. Totally impractical, not realistic at all. That's why I put this one here to kind of force us to do it this way. On number 6, even though it's a 5, I don't want to do that 5 times. So this theorem should still save us some time. If we're doing exponents that are bigger than 2, really, even if I went to a third power, I would not do it by hand. So this theorem is saying if you decide to raise a complex number to a power, that power being n, then there are 2 steps to get the polar form of that complex number to that power. We're going to raise the r to that same power and multiply the angle times the number of that power. That's it, those 2 parts. That's way easier than distributing 20 times or even 5 times. So for number 5, I've already done most of the work for us. I put this number into polar form. So I did that by finding the r value using Pythagorean theorem and finding the angle using tangent. I got r is root 2 and theta is 45 degrees. So now we're ready to start. If I were to raise this to the power of 20, so let me do that on both sides. Power of 20, power of 20. The theorem states that we're going to raise the r to the power of 20 and then we multiply the angle times 20. Let's first focus on the root 2 to the power of 20. You can do this in the calculator. I do also have a little bit of a tip, kind of a shortcut in some cases that might be helpful before you reach for a calculator. Keep in mind that a square root is the same as an exponent of 1/2. So this is the same as 2 to the power of 1/2, that's the square root of 2, then to the power of 20. Next, if I have an exponent on an exponent, they can get multiplied. So this is the same as 2 to the power of 10. Now, of course, in this case, I still need a calculator to figure out what that is, but sometimes knowing that trick can actually make it easy to do this part by hand, and you may not need a calculator. But let's go ahead and pull up a calculator to find what 2 to the power of 10 is. 2 to the power 10. 1024. Next thing that we have to figure out is the angle. Now I have 20 times 45 degrees, which is going to get to be a really big number. Sometimes I find that it's easier to multiply if I work in radians because the fractions will actually reduce really nicely. So feel free to use radians if you think that you feel that same way as me. I'm going to do them side by side just to show how there could be an advantage to working in radians. 45 degrees is the same thing as pi over 4 radians. And so I can immediately multiply these without any calculators at all. 20 pi over 4 reduces to 5 pi. And if you remember how pi and 2 pi work on the circle, 5 pi is coterminal with 1 pi. So I can reduce it immediately to just pi before I finish my answer. If I did this in degrees, there's no way I would immediately know that it's equal to 180 degrees. I would definitely need a calculator for that. So just keep in mind there could be some advantages to radians. Let's do this in degrees though, because I feel like that's what most of us are comfortable in. So 20 times 45 degrees gives us 900 degrees, which is way too big. So to reduce it, we're going to remove extra full circles. So I'm going to subtract away 360 degrees at a time until it becomes smaller. So let me do 900 minus 360. Still too big. Let's do that again. There we go. 180 degrees. On the topic of degrees versus radians, you're welcome to use either one. Just make sure if you use degrees that you label your units by doing the little degree symbol. Otherwise, I would assume it's in radians. So we have our answer. Basically, we have the new r for the complex number raised to the 20th power, and we have the angle. So all we have to do is put this into polar form. So 1024 cosine of our angle plus I sine same angle. And that's our answer. This is equal to 1 plus I to the 20th power. Okay, let's do the second one a little bit faster this time. So finding the r, we're going to do Pythagorean theorem. Remember that trick I just talked about? If you have two numbers that are multiplied under a square, you can distribute it. So 2 squared and then root 3 squared. Now let's find the angle using tangent. $30. And now to raise it to the 5th power, we have 2 steps. Raise the r to the 5th power, and then multiply the angle times 5. Now we just write our complex number raised to the power of 5 in polar form to wrap up this question. Let's suppose that I did want my answer to be in rectangular form, a plus bi, but I used polar form as a shortcut to get there so that I did not have to multiply 5 times. I can convert back to rectangular by using the values from the unit circle. I need to know what the cosine of 150 is and what the sine of 150 is. Cosine of 150 degrees, that's the x value at 150, is negative root 3 over 2. And sine of 150 is 1/2. And then if I distribute in the 1024, it gets reduced with the 2 on the bottom of each of those fractions, and I have my answer in rectangular form. Here are 2 different forms of the same answer. In both cases, these are the answer to the question that was originally posed. Okay, one last theorem, and that is to root a complex number. This one is the one that looks the most scary And it looks really difficult, but just like the others, we're just simply plugging numbers into the equation and simplifying as we go. So let's ignore this for just a moment and go down to the actual question and see what kind of information we can pull from it before we use this monstrosity of an equation. So here's our first question. This one says solve the equation. Z cubed minus 1 equals 0. This notation right after the equation is telling you that z is a complex number. If z was only allowed to be a real number, meaning no i's, the answer is 1. 1 plus 0 I is the answer to this question. But if we're allowing z to be complex, then there's actually more than just one answer to this question, which is kind of mind-blowing the first time you hear it. But in general, there's always going to be n roots of an nth root question. So for example, when we do square roots of real numbers, like square root of 4, square is a 2, so a 2 root, you get 2 answers, 2 and negative 2. So every time you do a root, there should be n solutions to that question. The problem is a lot of times they are complex numbers. So if we're limiting ourselves to real numbers, we may only get one answer and think, oh, we're done, that's it. But there's actually a couple that are hidden that have I involved, and this is how we find them. Looking at the equation at the top of the screen, let's just take it very slowly and look at any numbers that we don't recognize or any letters at all, actually. I see an n, which is described as the root. So in our question number 7, we're doing a cube root, which makes the n 3. So I'm going to go ahead and write that down. I should always see these 4 numbers in your questions as you're trying to solve them. I will be looking for r, theta, n, and k as you set up these questions. So follow along with me with my setup. I promise it makes everything so much easier. The next thing is z, but that's the complex number, in this case 1. So I'm just going to skip that for now. Then on the other side we have r, which we recognize as the hypotenuse of the triangle. So if we can find that, we'll have r. Then I see theta, which is our angle we've always been finding. So far nothing is new. K is new. K is basically a counter that tells us how many roots in we are. So like, am I at the first answer, the second answer, the third answer? The thing is, in a lot of applications of labeling things in real life, in science, in computer science, in math, for some reason we start with an index of 0. I actually don't have a solid answer for why we do that, because I could just change this formula and make it start with a 1. But even in programming, we start with an index of 0. So k, as our label for which root we're working on, is going to start at 0 for the first root, and then it goes to 1 for the second root, and then to 2 for the third root. And it's counting how many answers you should get. So if we're expecting 3 answers, I should just stop once I have 3 different numbers for k. So there's my k values. And it looks like everything else is kind of repeats of what we've already found. So I think we're ready to actually start this question. Down here, we need to first figure out our r and theta. But just like one of the questions before, if we drew the complex number, I think we can find the r and theta very fast. The number that we're actually finding the root for is just 1. 1 plus 0 I is the complex number. So if I graph it, it's 1 in the real direction and 0 in the complex direction. So what's its distance from the origin then? 1 unit. That's the r. And the angle, 0. So the angle 0, the r is 1, n is the number root, cube, and then k is a counter that counts up how many roots we have found. So now we've actually done all the hard part of the math. Everything from here is just going to be plugging into this formula, but we're going to do it 3 times, which is the part that feels a little bit exhausting, but the work itself is pretty straightforward. So let's start with the first answer. So I'm going to say for k equals 0, and I'm just going to work my way across the equation, one step at a time. So the first thing I see is nth root of r. So cube root of the real number 1. Then parentheses, cosine. Then the angle, 0 degrees. Next, our k value. For this one, we're working with k equals 0. Times. Now, the formula says 2 pi, but you're welcome to use 360 if you're working in degrees. So let's write that down actually, so that you know to do that later. This is in radians. You can use 360 degrees if theta is in degrees. Okay, so I'm going to use 360 then, since my theta is in degrees. Then it says divided by n. Our n was 3. Next, plus I sine. And then here's where I get a little bit lazy with my notation. Look at these two angles in the formula. They're exactly the same thing. I don't want to write it twice. I'm going to do the exact same work in both of them. So what I tend to do is I'll just write parentheses ... because I'm just going to be doing the same thing over again. No point. You can write it out if you'd like to. Okay, so now let's do a little bit of cleanup and we're basically done. So cube root of 1, the real number 1 is 1. Then we have cosine, and then let's figure out what our angle is. On top we have 0 plus 0 divided by 3. That's just 0 degrees. And then for the sine, we use the exact same angle. So that one's also 0 degrees. Okay, we're done with the first root. And actually, fun fact, this is the real root that you normally would have come up with on your own. Cosine at 0 degrees is 1, and sine at 0 degrees is 0. So this is that real root that was just equal to 1. What that means is the other two roots we should come up with are going to have a mixture of a's and b's because they're the complex roots that we normally couldn't find because we didn't really have a way to find them. Okay, we're going to change our counter. So k is going to go up to 1 this time. And we just repeat, fill in the blanks. So at the beginning of our formula is nth root of r. That will be the same every single time. Our theta was 0 degrees. K is now 1. And then I'm using 360 degrees instead of 2 pi divided by n. Plus I sine ... Now we clean up this angle inside and we're done. Cube root of 1. Now inside of cosine I have 0 plus 360, which is 360, divided by 3. So 360 divided by 3 is 120. That is our angle for the second root. Okay, and last one, let's find that third root. We're going to do k equals 2, then cube root of 1, inside of the cosine is 0 degrees, plus k times 360 divided by n. So the only thing that has changed each time we write this is the k. So this time to resolve that angle inside, it's 360 divided by 3, which is 120, and then times 2, 240. If you're uncomfortable doing that in your head, you can use a calculator. Should get 240. So my final answer is 1 cosine of 240 plus I sine 240. And then as we've said before, if you were just using polar form to use these theorems, but you actually wanted your answer to be in rectangular form, which is the standard practice for communicating about complex numbers, you can change it back to rectangular form by just plugging in the value for cosine and for sine at that angle. So for example, for the second root, where k was 1, cosine at 120 is negative 1/2. Sine at 120 is root 3 over 2. So I can turn it back into a plus bi form if I need to. I don't think I'm going to ask you to do that. I don't think Math Excel will either, but it's more of just in case you need to know it or if you were thinking whether you could. I have one last practice problem. I'm just going to kind of walk through it really fast, just doing the practice so you can follow along with me and then check your answer at the end. This one is asking for the square roots of this complex number. So I'm going to fill in my values before I actually fill in the formula. Square roots mean n is 2. That means that we should have 2 different digits for k. It always starts at 0 and counts up by whole numbers. So it'll only take on the values 0 and 1 this time. To find the r and the theta, you repeat exactly what we did all the way through the notes, using Pythagorean theorem and tangent to find those values. I've got everything set up now to fill into DeMoivre's theorem to find the 2 roots that this question is asking for. Double check your r and your theta and then plug everything in with me. First thing is the square root of the r value. That's going to be the same in both. Next, we're trying to figure out what the angle is inside of cosine. The angle formula was theta, in this case 30, plus k times 360 over n. So the only thing that changes from one root to the other is the k value. Root 8 can also be written as 2 root 2. In our first angle, 30 plus 0 divided by 2 would be 15 degrees. So that root is done. The second one is 30 plus 360, so 390 divided by 2. 195, I think. Let's double check. Yep. So our second root is done. That's everything I could possibly show you about complex numbers and polar numbers, their relationship with each other, and all the various theorems that you can use as shortcuts for the algebra. So good luck. Thank you for watching.